Good morning, ladies and gentlemen. I hope you guys are all doing well today. Happy Star Wars Day. May the 4th be with you. It had to happen, guys. And in honor of the occasion of Star Wars Day, we're wearing the scarf that is the entire opening text of Star Wars A New Hope, which is one of the classics. It's an awesome movie. So wearing that today in honor of May the 4th. So, ladies and gentlemen, today what we're going to do is look at the work energy theorem. So, work energy theorem is based on the idea that another definition of work, because we've already looked at the definition of work is equal to force times distance cosine theta. However, we can also look at definition of work as either the ability to do energy, or when we have a change in energy, work has been done. So that's going to be our focus for today. Now, please enjoy the pun with your notes. So renewable energy, I'm a big fan. Get it? Get it? Yeah, it's good. Although one thing with these wind turbines, you have to keep in mind that they are not perfectly green energy because it takes a heck of a lot of carbon, fossil fuel based stuff in order to build them and transport them. Sometimes if you're driving around Valley View and Fox Creek, sometimes you can see these things on a truck, and it takes a lot of trucks to get these things up there and a lot of stuff to make them. So they're not perfectly green energy. Okay, just despite what some people will tell you. Okay. Well, they also sometimes turn birds and bats into soup, so watch out. There's that too. All right, so ladies and gentlemen, let us begin with work energy theorem. So, once again, remember, ladies and gentlemen, that if you're going to have a force applied to an object, and if it is going to either cause or hinder the displacement of the object. So that is our work is equal to force times distance times cosine theta. So that's the previous definition of work that we were looking at. We're going to look at another way to look at work. So we can also look at work as a change in energy. Okay, so keyword change. Now remember, delta is equal to change in. This is on your data sheet, and you can find it at the lovely location of right there. Okay, as you can see, your work is equal to delta E. Okay. So, ladies and gentlemen, delta is change in, work is in joules, delta E is our change in energy in joules. Now, this is the expanded form. Our delta E is equal to the final energy minus the initial energy in a system. So that's no different than when we were looking at delta V. Our change in speed is equal to our final speed minus our initial speed. So that is something you guys are going to need to remember there. Okay? And EF, final energy, EI, initial energy. Okay? So this whole equation and concept is known as our work energy theorem. And now work is going to be done when there's any change in energy. It doesn't matter how the energy is changing. So we can be going from an increase in kinetic energy. We can be going in a increase in gravitational potential. So if I grab my T here and I lift my T, well, there's a change in energy. So I am changing my gravitational potential energy as I lift up the T mug. Okay. We could be talking about speeding up an object. There's going to be an energy change there. Okay. We could be talking about slowing down an object. There's a change in kinetic energy there. We could be talking about burning something. We're going from your stored energy to kinetic energy. So anytime there's a change in energy, you are going to be having work done. Okay, so these are just some of different examples. So when you're lifting something, increasing its gravitational potential, there's a change in speed, so you're changing your kinetic energy. You're doing work on a spring if you're going to be compressing it or stretching it and then letting it go. Okay, so now in Science 10, you've already will have learned about the different types of energy as far as kinetic and potential. You will have already seen these, so I do kind of expect you to recognize these equations from last year. So we've already talked about our elastic potential energy with your EP is your 1/2 kx squared. So these equations here are going to be review for you from last year. So where your kinetic energy is the energy of an object that is in motion. Okay, so any object that's moving has kinetic energy. And EK is your kinetic energy in joules. N is the mass in kilograms, and V is the velocity in meters per second. You can also find this equation right there on your data sheet. Okay, so you don't have to memorize that one. Okay. So once again, that's formulas review from last year. And the other equation that is a review from last year as well is your gravitational potential energy equation. Now, this equation is when you have a mass and it's at a vertical height. So that means it has stored potential to do work. So as you guys have seen plenty of times in class when I've dropped this thing, we're doing work because we're converting potential to kinetic. So this thing right now has potential energy. My T has potential energy. Not only is it potential to do work, it has potential to convert into kinetic energy. It also has potential to make a huge mess if I drop that. It won't be the first time I will have dumped T all over my office and starting online education. All right, so once again, EP is our potential energy, the stored energy, and that's in joules. M is the mass in kilograms. And G is 9.81 meters per second squared. That has not changed. And H is the height of an object. Now, this is scalar. Energy is scalar. So you do not need direction on any of these energy terms. They're scalar. Okay. So, ladies and gentlemen, okay, so we've looked at a few different types of potential energy. However, there's many different types. There's more than just gravitational and elastic. For example, energy can be stored in chemical bonds. So, for example, think about food. I like food. I like food a lot. So when we think about food, well, food is chemicals, essentially, that our body has the ability to digest and make use of. So when we are going to eat something, we're going to be getting the energy out of that food. And how does that food store energy for us to use? In the form of chemical bonds, in the form of chemical potential energy. So that's a very classic example. All right. Ladies and gentlemen, ready to rock some math? Of course you are. All right. So, ladies and gentlemen, a toy ball has 63 joules of kinetic energy. What would be the new kinetic energy of the ball if the mass is doubled and the speed is reduced to a quarter? Okay. Recognize this type of question from the previous couple videos? Yep. This, ladies and gentlemen, is a substitution equation, what I like to call math wizardry. And we are going to, once again, very important skill for Physics 30. We do this all the time in Physics 30, so it's a good time to practice. Now, this is our original information here. And then we are going to be looking at our modified. Now, this equation here, this question just kind of to warm you guys up, getting used to our EK equation. So our original EK, that's supposed to be an E, is 63 joules. Okay. And we'll also remember, ladies and gentlemen, that our EK is equal to 1/2 mv squared. Now, if EK is equal to 63 and EK is also equal to 1/2 mv squared, that means that 63 joules is going to also equal to 1/2 mv squared. Okay, so, well, my mass prime, now remember that prime, this little tick up here, means that it's the modified or the after object. So it is going to be twice that of our original mass. Now, our original mass is going to be m, and our original speed is going to be v. We don't have those values. Okay? And our speed prime, so our speed after modification, is going to be a quarter of what it was. So it's going to be 1/4 v, or v over 4. Both of these are mathematically the same. Okay? So, ladies and gentlemen, what we're going to do is we're going to take our EK is equal to 1/2 mv squared, and I am going to substitute these values in there. Okay, so my EK prime, now once again, prime is after modification, is equal to 1/2. Now m, 2m, okay, I'm going to substitute that in for my m, is going to times v over 4 squared. Okay, so ladies and gentlemen, what we're going to do is we're going to solve what we can here. I'm just going to leave the 2m for now, but what I am going to do is I'm going to square this. Okay, so when we square this, ladies and gentlemen, we are going to have to square this guy too. Okay, so we wind up with v squared, okay, because when we're squaring this, it's squaring the inside of this bracket and squaring this guy. So it's going to be v squared over 16, because 4 squared is 16. So what I'm going to do now is I'm going to factor out my 1/2. I'm going to factor out the m, I'm going to factor out the v, or I can go the other route and factor out 2 divided by 16, because I really want to get this 1/2 mv squared on his own there. All right, I'm just going to scroll down here so I've got some more space. Okay, so my EK prime is going to equal, I'm going to factor out this 2 over 16 here, 2 over 16 times my 1/2 mv squared. Okay, so I factored out the 2 and I factored out the 16, divided by 16. So now what I can do is, well, I can just simply take my 63 here, I nearly said 36, 63 joules here, and replace that with this, because remember, 63 joules is equal to 1/2 mv squared. 1/2 mv squared is equal to 63 joules. So I take my 2 over 16 and I multiply that by 63 joules. Once you multiply all that together, you're going to get a kinetic energy of 7.875 ... joules. And then sig digs, as always, ladies and gentlemen, our EK prime, I'm going to put this prime back there, is going to be equal to, with your sig digs, 7.88 joules. Energy is scalar, ladies and gentlemen, so you do not need direction. Cool beans? Cool beans. Alrighty-o. So, ladies and gentlemen, that's that first question. The math wizardry up there is very important for Physics 30. So if you need help with that concept, let me know and we can go over that. All right. Next question, ladies and gentlemen. What work is done by gravity as a 2 kilogram pendulum moves from a height of 0.75 meters to its equilibrium position? Okay, so let's think about what we've got here. Well, we have a height that the object is going to be moved. We have a distance that we are moving this. We're moving it from here to here. Okay, we're doing work. We know distance. So there's two ways we can go about this. Well, work is equal to force times distance times cosine theta. And we've got gravity going here. So we could go this way if you wanted to. If on a question, on an exam, if we had exams, so assignment, if you had distance and you had a question like this, absolutely, you could definitely go this route. But because I've already shown you how to do that, we're going to look at how to do this from the concept of conservation of energy. Okay, conservation of energy. Work energy theorem. Conservation of energy is the next video. Okay, so ladies and gentlemen, I have the mass of the object of 2 kilograms. Okay, so moves the work done by gravity as the pendulum moves from a height of 0.75 to its equilibrium position. Well, here's our pendulum, and here's our equilibrium position. Okay, so remember, a pendulum is any object held onto a string that's going to be swinging back and forth, back and forth. Normally, I'd start swinging my keys, but I don't have a set of keys. Maybe I do. Hold on one second. I'm going to go find my keys. I'll be right back. Okay, I do have my work keys. Okay, so my work keys are going to be my pendulum. As funnily enough, in class, my work keys are always my pendulum. So right now, my work keys are hanging at their equilibrium position. Well, now, if I move them up here, okay, right now, the keys have gravitational potential energy as they're held right here. Now, when I release them, their potential energy is going to be converted into kinetic. So notice how when the keys are swinging, we're going potential kinetic, potential kinetic, potential kinetic. We're going to talk more about that in our next video. But for now, we want to know the work done by gravity and moving the keys from here to here. Okay. So you can use work as force times distance, but for this question, what we're going to do is we're going to go that work is equal to delta E. Okay, so let's think for a moment what is happening. Okay, so our work, well, what energy is up here? Gravitational potential. Absolutely. And ladies and gentlemen, what energy is being lost as it comes down here? Gravitational potential. Up here, right up here, what kinetic energy does that object have? Well, none. Down here, well, all the energy at the very bottom is going to be kinetic at that point. Okay, well, however, I have mass and I have height, but I don't have speed, so I can't use kinetic energy. If I had the numbers, I could, but I don't have the numbers, so I'm going to use my change in potential energy. Okay, so ladies and gentlemen, my work is going to be equal to my EP final minus my EP initial. Okay. Now, I'm going to be showing you guys another trick. If you guys want, you're welcome to go and calculate EP MGH with F, EP equals initial, multiply that all together, then subtract afterwards. But I want to show you guys for this question another method that is going to be useful for you in future. Okay, and that's going to be pulling in factoring from math. Now, factoring is going to become something very important when we look at our next video, when I don't give you a mass. Yeah, I do that to you guys. All right, so now MGH, okay, final minus MGH initial. So let's think about this. The object has a mass of 2 kilograms, and our G value is 9.81 meters per second squared. Is the mass of the pendulum changing? No, it isn't. Is G changing? Are we zooming off to Mars in the middle of this question? No, we're not. So when we're looking at my keys, up here, the mass is the same, The mass is the same. G is the same. G is the same. What's different? The height. So HF and HI are different, but M and G are the same. So think back to math, ladies and gentlemen. I can factor out mg from each of these terms because they are identical. So mg times hf minus hi. Okay, so I have then factored that out. Now I can put my numbers in. So my mass is 2 kilograms, and my g is 9.81 meters per second squared, and then hf and hi. Well, ladies and gentlemen, look at our diagram. Here we have our equilibrium is 0.5 meters, and up here is 0.75. This is our HF, and that is our HI. Okay, so again, when we look at these keys currently have gravitational potential energy at the bottom? Yeah, of course they do. They still have gravitational potential energy. If I drop them there, they still have the ability to do more. Okay, so my HF, 0.5, and then minus the height of 0.75. I'm going to plunk this all into my calculator, ladies and gentlemen, and I'm going to get 4.905 ... joules. Okay. Now, ladies and gentlemen, why did I drop that negative? Because energy is scalar. Absolutely. You don't need your negatives on scalar quantities. Okay. So the amount of work done by gravity, ladies and gentlemen, with your sig digs is going to be 4.9 joules. Cool beans? Cool beans. So if you really want to, ladies and gentlemen, once again, you are welcome to go EP final equals MGH, and then EP initial equals MGH. Calculate these separately and then subtract them. You can do that in this question if you want to show your work that way, but just keep in mind there are going to be scenarios where in the future where you are going to have to do something kind of like that, just because of the lack of mass. And we'll get to that later. All right. I think that's the next video we're doing that. So, ladies and gentlemen, on to our next question. Okay. Question number 3. All right. So we have a 65 kilogram snowboarder. So we have our mass, has a speed of 2 meters per second at the start of her run. So her initial speed is 2 meters per second. At the bottom of the hill, she has a speed of 15 meters per second. Okay. What was the work done going down the hill? Okay, so ladies and gentlemen, in this case, can we use this? No, we can't. We cannot use this because we have no distance. Okay, we have no distance, and because there's no distance, and there's no way to get distance with the numbers you've been given, you have to use your work equals delta E in this case. Okay, so sometimes questions will force you into a particular method of solving the problem based on the numbers that you've been given. Okay, so we can't use this, but we are going to be able to use our work is equal to a change in energy. In this case, it's our kinetic energy that's changing. So work is equal to my delta E, and delta is expanded. Okay, so my EKF minus my EKI. Okay, sounds good? Okay. Now I'm going to do the same thing here that I did last time. I'm going to substitute the values in. I'm going to do some factoring here. Okay, it's an important skill that you guys are definitely going to need for next year. So my EK is equal to 1/2 mv squared, and my V final, my EKI is equal to 1/2 mvi squared. Okay, so ladies and gentlemen, let's think about the scenario again. 1/2 is the same, m is the same, because our mass of the snowboarder isn't changing and the 1/2 isn't changing. I can factor out the 1/2 m. Okay, so work is going to equal 1/2 m vf squared minus vi squared. Okay, so 1/2 m times vf squared minus vi squared. Alrighty-o. So all I've done is I've just factored out the 1/2 m from both of those terms because they're identical. And once again, if you really want to, you're more than welcome to find EK final, EK initial in separate calculations and then subtract them. So with this, 1/2 times my mass of 65 kilograms times my VF squared, which is, so 15 squared minus 2 squared. Watch your calculators, ladies and gentlemen. Make sure you're following those BEDMAS rules when you're plonking this into your calculator. And once you've done that, you're going to wind up with 7, I dropped a 1, 7182.5 joules. Ladies and gentlemen, sig digs, I want 2, because this guy here has 2 sig digs. So we're going to go, work is 7.2 times 10 to the 3 joules. Another way that you can communicate this, ladies and gentlemen, is also 7.2 kilojoules. Both of these are correct. So it just depends. Do you want to put your numbers into sig dig or into scientific notation for sig digs, or do you want to put it into or convert units to get sig digs? Both of these are acceptable. That's also why I insist on you writing your units. Because if you write 7.2 times 10 to the 3 or 7.2, well, if I happened to do my answer key to kilojoules, which I often do, and I see this, I don't know which one did you use, right? I could then have to go back and look and see, okay, and figure out what your units are. But that's not what you want. You're going to lose half a point that way, right? Your units. Okay? So that's where units become so important. And the thing is, when I'm marking, well, I know what I'm marking. I got the question, I've made the answer key, I've assigned the question. So I know what it should look like. However, let's think about it once you're an engineer or something. Well, people can't assume what units you're using. Okay, so even with your cars, when you look at pressure, they're going to be telling you if the pressure in your tires is in kilopascals or psi. So they always have to have your units there. The numbers are going to be different. All right. So, ladies and gentlemen, enough of my usual rant about units. You hear that all the time. So, ladies and gentlemen, we've got some practice problems here for you guys in your workbooks to work on. So these guys here are going to be Science 10 review. If you are 100% comfortable with your rearranging of your EK equation and your EP equation, then awesome. You can just skip those ones. And then these ones, okay, are that's supposed to be a P, and it turned out to be an R. These guys are your Physics 20 questions, and these guys here are your ratios, okay? So those are your math wizardry questions. Sounds good? All right, ladies and gentlemen, I hope you have an excellent day. May the 4th be with you, and take some time out of your day to watch some Star Wars, preferably the original 3, because they're the best. I know, practical effects, but also keep in mind they do break the laws of physics, but we will forgive them that because Star Wars is incredible. There's no sound in space. So when the Death Star explodes, it doesn't actually make a noise. So there's no noise with that. And there is no fire in space because there's no oxygen. So the Death Star isn't going to blow up in a big fiery ball. But we'll forgive George Lucas that. All right, ladies and gentlemen, you guys have a good day. I can't stop this. There we go. Yeah, one of these days I will figure out the tech. Now it's being slow and I can't stop it. Come on. Really, technology. I'm completely overwhelmed by all the teachers using it right now. Okay, now we're going to go. Have a good day.